Hey Science Nights, today we're going to be discussing topic 2.3 of the electrical unit, which is analyzing and building electrical circuits. This isn't really a new concept because I've been kind of showing you on and off electrical circuits throughout this unit, but this is more just to kind of wrap your head around how to draw them, what the symbols mean if you don't already know, and we'll do some recaps on those, as well as different types of circuits and how you can draw them. So the differences between what are called parallel and series circuits, and we'll get to all of that today. So first of all, when you draw circuits, as I've been drawing them throughout the unit, you use what's called a schematic or a schematic diagram, like the one I've got here. And this diagram here has several parts to it. These are all ones that you should be familiar with. For example, this right here, you should know is your battery, right? You've got your positive electrode here, your cathode. Your anode on the other end is your negative end, and it's drawn with two long and two alternating short and long lines to indicate that's a battery. If it was a cell, we would simply use this symbol, like I've mentioned before, which would then be a cell, because remember, a battery is a multiple set of cells, and a cell is a single packet of chemicals that can convert, chemically react to produce electricity. There are at least 1, 2, 3, 4, 5 other structures on this diagram. If you want to pause the video right now and just see if you can name what each of those structures or what those objects are, that would be maybe a good idea, but I will go through them very quickly right now. Okay, the circle with the A inside of it, as we mentioned in the last lesson, which was in 2.2, that is an ammeter, which is going to be a meter that is going to measure the amount of current, the amount of amps that are running through any circuit. This structure here with the zigzag lines, we talked about that, I believe, back in 2.1, if I'm not mistaken. This here is a resistor. This is a resistor, something that is going to be put in the circuit to create resistance against the current, but that's a resistor. And again, we did mention what we had. We also talked about something called a variable resistor or a rheostat. That would be a slightly different symbol. It's going to look something like that. That's a rheostat. Actually, wouldn't be on the bottom here. Let me redraw that. A rheostat would be drawn, that line would be drawn on the top. So if I had that symbol, that would be a variable resistor, which would be like a volume control or a dimmer on a light, also known as a rheostat. So that would be that symbol there. This symbol here should be pretty self-explanatory. We've talked about that symbol quite a bit. That's your switch. That's going to turn the circuit on and off. Down here we've got a circle with that little squiggly M in it. That's going to be a lamp. We talk about lamps a lot, and remember, if it's a load, technically if you had like just a generic load, sometimes if you just see like a load, I think this could be anything that's being powered by the circuit, you sometimes will see this symbol, just an X running through the circle, and that would just represent a generic load, something that's being powered by the circuit. And then finally, you've got this circle with a V inside of it, which has lines on before and after the load, because that is measuring the voltage drop before and after, across a load. That's going to be your voltmeter. That's going to be a voltmeter there. So these are all symbols that you've seen in other lessons in this unit, and you can see that I've drawn this circuit. And for this part of the unit, you're going to have to do a little bit of drawing of these circuits of your own to actually draw one out to make it look, all nice and pretty, and make sure not that it looks nice, but also that it actually works. And depending on what type of circuit you're dealing with, and again, you can see some of these schematic diagrams get very intricate, very complicated. We're not going to get anything close to that here in grade 9, but the symbols are ones that you should be familiar with. And if you look in your textbook, there is actually there is a table in your textbook on page 312 that gives you a list of all the different symbols. So if I'm asking you to draw a circuit as part of an assignment or requested in the textbook, please refer to this table on page 312. That will give you sort of the crib's notes, as it were, symbols that you would find in a that you might use in an electrical schematical diagram. I also believe there's an advanced symbol table at the back of your textbook. It's in one of the appendices at the back of your textbook. There's another one that has some kind of more more one-off kind of symbols that might not be as well known. Like for example, on this diagram here, or on this table here, you'd see down here at the bottom, there's actually a symbol for a motor. A motor, by the way, if I had a motor, and we're going to get to motors later in the unit, so this is kind of a good one to know as well. A motor is represented like this. If I see that symbol, a circle with sort of 3 dots inside of it, it's still a load, but it's specifically now a motor. That's a motor that's being powered by a circuit. So that's you might have use for that at some point. Another symbol that's on here that I kind of like is this one here. We talked about this early in the unit. We talked about this in section 1.3, the use of fuses, how some devices have a fuse. That symbol there would be a fuse. And again, remember, a fuse is a device that's in a circuit, and if the circuit overloads, the fuse melts and then basically cuts and breaks the circuit so that we don't get a massive surge of electricity or a short circuit or an electrical fire or something like that. So this table here on 312 is going to give you all those different symbols. Now, there are 2 main types of circuits that I'd like to kind of introduce you to today. I've drawn a lot of circuits. All the circuits I've drawn thus far have been what are called series circuits. They're all circuits that basically the electrons have. That isn't true. I've drawn a couple of parallel circuits. Actually, this one here, technically, there is a parallel aspect to it because there is a parallel line running off of here. But other than the voltmeters, I haven't really shown you any circuits that have parallel configurations. All the circuits I've drawn have been series circuits. And a series circuits, by definition, means that there's only one pathway for the electrons to flow through. So in this case, my electrons just sort of go round and round and round and round. In a parallel circuit, you've got the electrons can choose different paths. So the way I like to explain this is it's sort of like Mario Kart. There are some courses in Mario Kart where you can take a shortcut. You can take the main course, but then sometimes it's like a little shortcut if you really know the levels really well. You can take sort of another method that might save you some time going that method. But in any case, a parallel circuit means that the electrons have more than one choice of which direction to go. So in this case, I've got on my series circuit, I've got 2 lights in a row on the same section of the circuit, whereas here I've got 2 lights that are lit that are wired in a parallel configuration. Now, why do you do that? Why is there a need to run a parallel circuit as opposed to a series circuit? Well, I'm going to show you by simply drawing one thing on the circuit. This circuit does not have a switch yet. If I had a switch there, and what if I had a switch here? Now, in this case, if I open up this switch, what's going to happen to the lights that are on the circuit? If it's open, there's no flow of electrons to the entire circuit has been broken. Basically, these lights, both of them shut off. So I only have one form of control off of everything that's on the circuit. Basically, one light goes out, they all go out. And an example of that would be like Christmas lights, or some kind of Christmas lights where you get when the one light bulb goes out in the strand, all the lights die. That's essentially a series circuit. If there's one break in the line of the circuit somewhere, there's one place where the electrons can't flow through, all of the items on that circuit basically shut off. That would be a real problem in your homes. Like, for example, if I had, let's say I have a bunch of pot lights in my house, like I have here in my basement. I've got a bunch of pot lights that are lighting me right now. If one light bulb goes dead on my ceiling, they don't all go out at the same time. I only lose one light. The reason why that's the case is because I've got a parallel configuration going on. Each light in my ceiling has a separate wire. So technically, if one light goes out, they don't all go out, right? So technically, if I have a light switch here, this light, this switch here is going to kill this light, but it's not going to kill that light over there. So depending on where you put a switch in a parallel circuit, you can actually have control over which lights you turn on or which loads you turn on and off. So for example, here I could put another switch there. And by doing that, I can control this device separately from that device. And that works in your home. Like you turn on one light switch in your kitchen, it might only turn on your pot lights. One light switch in your kitchen might turn on the light over your island. One light switch in your kitchen might turn on the light above your kitchen table. They're all on. They're all part of a circuit because they might all be. They're all part of the same circuit in your house potentially, especially if they're on the same circuit in your circuit breaker. But I have different switches that control each of those lights in, say, my kitchen. For example, a bedroom, you turn on one light and it turns on the light in your bedroom, right? But in a bathroom, you might have two different switches. You might have a switch that turns on the light, one that turns on a fan. They're on, but they're both powered by the same part of your circuit breaker. Like if you blow your circuit breaker in your basement and you trip a breaker in your house, both the fan and the lights go out because they are both. There might be your circuit breaker might be here, right? So the circuit breaker, if it breaks, shuts off everything. But normally your circuit breaker is connected, right? Unless you trip your breaker. And then when the electricity gets to that room, there might be one switch that controls the fan in that room, and there might be a switch that controls the lights in that room. And those are the reason you can do that is you're on a parallel circuit as opposed to a series circuit. So again, like I've just discussed, here's your diagram in the notes where we discuss this, and basically it's asking you, is it possible to shut off only one light in a series circuit? So is it possible to shut off a single light in a series circuit based on what I've said? You can answer right up here. Give me what you think your answer is. So can you only turn off a single light? In this case, can I only turn off a single light in my series circuit? The answer is no, I can't. If it's a series circuit, if I kill one light, I kill them all. They all get shut off at the same time. What about in a parallel circuit? Can I shut off a single light in a parallel circuit? Quickly give me your guess up here. Is it going to be possible to shut off a single light in a parallel circuit? And the answer is yes. It is able, depending on where you put your switches, you can have multiple switches in a parallel circuit which control each load or each light in a circuit. And again, where would you put the switches? Again, if I had a switch, if I don't have these switches here, and it all depends on where you put your switch. If I just have a switch over there, then this parallel circuit functions like a series circuit. If I kill the switch here, then all my lights on the circuit will die, right? Because the electrons are basically disrupted no matter which path they're going to. However, if I don't have a switch there, and I put a switch there, and I put a switch there, and each of these two paths are controlled individually. If this switch opens up, the electrons can't flow this way, but they can certainly flow that way through the other light. If both the switches are open, then basically no electrons are flowing anywhere. So that's basically that. Quick little review video for you. If you check out the review video up here, it's going to basically walk you through series and parallel circuits just one last time to kind of give you a head around it. The math in this one is maybe a little bit more complicated than we need to go through, so don't get bogged down in the math. They're going to go through calculations of how you calculate resistance in a series versus a parallel circuit. That'll be more something we're going to cover when we get to Science 30, but the information about a parallel and a series circuit in the video is very accurate. So even if you just want to watch that section, if the math gets a little bit complicated at the end, you can kind of cut it short if you like. But yeah, give that video a watch, and at least the beginning of it, it'll give you a good indication as to what's going on review-wise for a parallel versus a series circuit. So what are some of the applications if I'm using parallel versus series circuits? Well, I've already talked about one. Your homes, depending on how you want a room wired, houses will have both series and parallel circuits. For example, there will be, there might be one room where you've got three lights that all turn on at the same time. So, for example, I've got a room where I flick on, maybe three ceiling lights all at the same time. they would be on a series circuit because they all turn on and off at one time. Um, but there would be such situations where we want parallel wiring, where we want to be able to separate lights. So, for example, in the kitchen, I don't want all my lights to go on in my kitchen at once. I just maybe want my nook light to go on, or I want my light over my island to go on, or maybe my under counter lighting in the kitchen or something to go on. The analogy would be if I had a series circuit in my entire house, then I would flick one switch and all the lights and everything would come on in my house at the same time, which doesn't make a lot of sense because that's a lot of extra power that you're drawing out of your house to light your entire home all at once. So houses are generally speaking have a lot of parallel wiring in them to basically allow you to light each room separately. A couple of other things that are more modern versions of electrical circuits are transistors are one. Transistors are basically solid state components that have layers of silicon. And we talked about silicon in Unit B. It's sort of a metalloid. It's sort of right in between where the metals and the non-metals are. It has some conductive abilities, even though technically it's not quite a metal. It sort of doesn't really know what it is. Is it a metal or a non-metal? But the silicon actually works. You put it in layers, and the silicone layers will actually act like switches. Sorry, I don't have my diagram anymore, but they act like the switches would in a circuit. And there's a great little video. The science behind it is actually really kind of intriguing, just how these molecules interact with each other, because it's actually a molecular interaction between these layers of silicone that actually tell the circuit to go on or off, and again, or the transistor to go on and off, and really kind of some fascinating stuff. So if you want to watch that video really quickly, might be kind of worth a watch just to see sort of the microscopic, microscopic doings of a transistor, because it is actually very interesting from that perspective. And the last one, example or application of a parallel or a series circuit I'd like to talk about are microcircuits or microchips or integrated circuits, which are basically, these are microscopic transistors. These are transistors on a very, very small scale that have basically revolutionized everything from our mobile devices that are in our hands or iPads. Basically, we live in a tech world now, and it's because of the microchip that we've been able to take technology and shrink it right down. And I kind of laugh when people see my old iPod, which isn't that old, but even by your standards, an old iPod is so thick, it's like crazy, compared to the old iPads that used to be so bulky. I mean, the technology is changing all the time, and the size of these microchips is allowing us to create smaller and smaller devices that have the ability to convert energy and be powered electrically. So that's it for today's topic. Homework today is going to be questions 1 and 2, questions 4, 5, and 6, 9, 10, and 11 on page 316 of your Science in Action 9 textbook. That's it for today. Thanks for tuning in, and we'll be back really shortly, and we'll be getting started on topic 3.1 next time. So you guys and gals have a great day, and we'll see you soon.